There's a phenomenon in the universe so strange, so deeply counterintuitive, that it seriously bothered the one man who seemed to have the cosmos all figured out. It was a bizarre connection that appeared to ignore the universal speed limit, linking tiny particles across enormous distances in an instant. This isn't a sci-fi plot. This is the reality of quantum mechanics, and it's the story of why Albert Einstein, the architect of relativity, called spooky action at a distance. It was a concept that threatened to break his beautifully orderly picture of the universe, and it sparked one of the biggest debates in the history of science. This is the story of that intellectual clash. A story that starts with a puzzle and ends with a reality that is far weirder than even Einstein could have believed. Imagine you have two coins, and you flip them at the exact same time, on opposite sides of the galaxy. The very instant one lands on heads, you know with 100% certainty the other has landed on tails. Not a second later. Instantly. This isn't a magic trick. It is a real feature of our universe that seemed to imply information was breaking the speed of light, a thought that haunted Albert Einstein. This is what he famously called spukhaftfernwirken, or spooky action at a distance, to show just how much this quantum connection unsettled him. It was like a ghost in the machine of reality, a phantom link that defied the very laws of space and time he had worked so hard to define. The clockwork universe and its challenger. To really get why Einstein was so uncomfortable, you have to understand his world. It was a universe run by magnificent, predictable laws. At the start of the 20th century, Einstein had given us a new cosmic masterpiece with his theory of relativity. Everything was orderly, and everything was certain. In Einstein's universe, nothing, not an object, not a signal, not a bit of information could travel faster than light. That was the absolute speed limit. It was the foundation of causality, the simple rule that an effect can't happen before it's caused. Einstein also believed in something called local realism. It sounds complicated, but it breaks down into two pretty simple ideas. First, locality. Things can only be affected by their immediate surroundings. A bowling ball moves because another ball hits it, not because a ball on a different lane moved. Second, realism. The idea that objects have real, definite properties, like a specific position or speed, whether we're looking at them or not. The moon is still there even when you're not looking at it. For Einstein, the universe was like a giant, intricate clock. Complicated, yes, but ultimately knowable and playing by deterministic rules. But just as Einstein was putting the finishing touches on his vision, a disruptive new theory was taking shape. Quantum mechanics. And it was anything but orderly. It described the subatomic world as fuzzy, based on probabilities, and fundamentally uncertain. Physicists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger were the pioneers of this wild new frontier, and their reality looked nothing like the classical world. In the quantum realm, particles didn't have definite properties until you measured them. Before you look, an electron could be in a superposition of many places at once, a literal cloud of possibilities. It was the act of measurement itself that seemed to force the particle to choose a single state. This built-in randomness was a direct attack on Einstein's worldview. It's what led to his famous line, "God does not play dice with the universe." He was convinced that the probabilities in quantum mechanics weren't a real feature of the universe, but just a sign that our understanding was incomplete. He figured there had to be some deeper, hidden rules, what he called hidden variables, that would bring back the comforting certainty he believed in. This disagreement set the stage for one of the greatest showdowns in science, and the weirdest, most bizarre quantum idea of all was right at the center of it. Entanglement. Quantum entanglement is when two particles become linked, so their fates are tied together, no matter how far apart they get. If you have two entangled particles, their properties are correlated. For instance, if you measure one and find it has a spin up, you instantly know the other has a spin down. The correlation wasn't the weird part. The weird part was how it happened. According to quantum mechanics, neither particle had a definite spin until you measured it. So, the act of measuring one particle seemed to instantly influence the other, even if it was light years away. This was Einstein's spooky action at a distance. It looked like a blatant violation of his cosmic speed limit, a kind of faster-than-light communication. For Einstein, this wasn't just weird, it was impossible. It was a paradox that told him quantum mechanics couldn't be the full story. The Great Debate and the EPR paradox. The rivalry between these two worldviews came to a head in a series of now legendary debates between Einstein and Danish physicist Niels Bohr. Who was the main champion for the quantum world? These debates, especially at the 1927 Solvay conference, were a true battle of giants. Einstein, with his incredible intuition, would cook up clever thought experiments to try and find a logical flaw in quantum mechanics, some way to measure a particle's properties without disturbing them, which would prove they were real all along. Again and again, he'd challenge Bohr with a new puzzle. And again, Bohr would think it over and find the hole in Einstein's logic, often using Einstein's own theory of relativity against him. Even though Bohr won the debates, Einstein wasn't sold. This wasn't just a gut feeling for him. He thought he could prove that quantum mechanics was an incomplete theory. In 1935, he teamed up with two younger physicists, Boris Podolsky and Nathan Rosen, and published what would become his ultimate argument, known as the EPR paradox. The paper presented a thought experiment meant to make the physics world choose. Either quantum mechanics was right, or Einstein's principles of locality and realism were. The argument was elegant. Imagine, they said, you have a pair of entangled particles shooting off in opposite directions. Let them travel light years apart. Now, because of locality, measuring the first particle can't possibly affect the second one, since no signal could travel between them fast enough. And here's the brilliant part. The EPR paper argued you could decide to measure the exact position of the first particle. Since they're entangled, you'd instantly know the position of the second particle. Or, you could measure the momentum of the first particle, and you'd instantly know the momentum of the second. The key was that you learned about the second particle without ever touching it. According to Einstein and his colleagues, if you can figure out the second particle's exact position, it must have had a real, definite position from the start. And if you could instead figure out its exact momentum, it must have had a real, definite momentum. Therefore, the particle must have had both a definite position and a definite momentum at the same time. But this is something quantum mechanics, through Heisenberg's uncertainty principle, says is impossible. For Einstein, the conclusion was obvious. These properties must be real. And if quantum mechanics couldn't account for them, the theory had to be incomplete. There must be hidden variables like a set of pre-written instructions the particles carried with them from the start. This would explain the correlations without any spooky, faster-than-light action. The particles weren't talking to each other across space. They were like a pair of gloves separated at birth. If you open a box and find the left glove, you instantly know the other one is the right. Not because of a spooky link, but because their handedness was set from the beginning. The EPR paper shook the world of physics. It perfectly highlighted the strangeness of the quantum world, but for decades, it was just a philosophical debate. No one knew how to actually run the experiment to see who was right. Was the universe locally real, like Einstein believed, or was it non-local and based on probability, like Bohr argued? Science was stuck, facing a huge question about reality with no way to find the answer. If you're enjoying this trip into a quantum mystery, make sure to subscribe and ring that notification bell. We explore the biggest questions in science every week, and you won't want to miss what we dive into next. The bell tolls for Einstein for nearly 30 years. The EPR paradox was just a philosopher's puzzle. Einstein's hidden variables seemed totally reasonable, even if you couldn't prove them. But then, in 1964, a brilliant and humble physicist from Northern Ireland named John Stuart Bell changed everything. Working at CERN, Bell took a hard look at Einstein's argument. He wondered, if these hidden variables were real, could you actually test for them? What he figured out was so important, it turned the whole debate from philosophy into real, experimental physics. Bell created a mathematical proof, now known as Bell's theorem. What it did was extraordinary. He proved that if Einstein's view of reality, the one based on local hidden variables, was correct, then the correlations between entangled particles could only be so strong. He found a hard limit, an inequality, that any local realism theory had to follow. Think of it this way. If the particles have preset instructions, there are just some statistical results that are impossible. But, Bell showed, standard quantum mechanics predicted that under the right conditions, those correlations would violate his inequality. Suddenly, it wasn't a matter of opinion anymore. It was a testable question. Someone just had to build an experiment that was precise enough to measure these correlations and see if they broke Beal's inequality. If the inequality held up, Einstein was right, and quantum mechanics was incomplete. If it was violated, then reality was even spookier than he'd imagined, and the universe was fundamentally not. It took a few years for technology to catch up, but in 1972, a physicist named John Clauser and his graduate student Stuart Friedman at UC Berkeley ran the first real test. Their experiment used calcium atoms to create pairs of entangled photons, particles of light, and sent them in opposite directions to be measured. The results were clear. Bell's inequality was violated, just as quantum mechanics predicted. Einstein's local realism seemed to be wrong. Over the next decade, Close's experiment was improved upon by physicists like Alain Aspect in France and Anton Zeilinger. They closed loopholes in the original experiment, separating the particles by huge distances and making measurements so fast that no light-speed signal could possibly pass between them. Every single experiment came to the same, stunning conclusion. The spooky action was real. The universe, on a basic level, is non-local. For their groundbreaking work, Close, Aspect, and Zeilinger were finally awarded the Nobel Prize in Physics in 2022, a testament to how important their confirmation of entanglement truly was. But the story doesn't stop there. Einstein's skepticism, while wrong on this point, was incredibly valuable. His constant questioning forced scientists to face the deepest parts of their theories, and led to the proof of one of nature's weirdest features. What started as a philosophical headache is now a key part of modern physics and the foundation for amazing new technologies like unhackable quantum cryptography and quantum computers. And, even today, the ghost of Einstein's spooky action is showing us new things. In an amazing breakthrough, scientists looking at data from the Large Hadron Collider found the first ever evidence of quantum entanglement inside individual protons. They discovered that the quarks and gluons that make up a proton are entangled with each other, acting as a single, connected quantum system across tiny distances. In another historic discovery at the LHC, confirmed in 2024, physicists also proved that top quarks, the heaviest fundamental particles we know of, also experience quantum entanglement. These massive, short-lived particles are still tied together by this instant connection, proving that spooky action isn't just a quirk of lightweight photons, but a universal rule of the quantum world. So, why did Einstein call quantum physics spooky? Because he believed, deep down, in a universe that made sense, one that was orderly, predictable, and local. He just couldn't get on board with a reality where touching a particle here could instantly change. Another one where across the cosmos, it felt like a bug in the beautiful cosmic program he had discovered, a spooky cheat code through the fabric of space and time. And yet, experiment after experiment has proven that the universe really is that strange. The connection is real, and it is instantaneous. Einstein, the man who redrew our map of gravity, space, and time, was wrong about this quantum puzzle. But in asking the tough questions, he accidentally set us on a path to a much deeper understanding of reality. He showed us a universe that's far more connected and mysterious than he, or anyone, ever thought possible. The spooky action he was so afraid of isn't a flaw in the theory. It's a fundamental feature of the world we live in. World tied together by invisible threads, connecting the smallest specks of dust to the grandest cosmic structures in ways we only just beginning to understand.